All right, so last time we started talking about TLC, thin layer chromatography, and then one of the things that we said when you have a TLC plate, you're going to put it in a solvent, you're going to put it in a developing chamber, a jar with a solvent in it, and what happens is the solvent is going to move up the plate. As the solvent moves up the plate, it's going to move the compounds with it. And then we talked about, okay, the rate of this compound going up the plate with the solvent depends on their polarity. Because the TLC plate, which is a silica plate, is polar. So the TLC plate is polar. Now, if you have a polar compounds on there, the polar compound is going to love the polar TLC plate. Polar likes polar. Non-polar likes non-polar. So the polar compound is going to like the polar silica plate. They're going to hang out together. They're going to interact strongly, so it's not going to move up the plate very fast. Because of that, it's going to have a small RF value. Now, if you have a non-polar compound, it's not going to like the polar plate, so it's not going to interact much. It's just going to whoosh, go up as fast as it can. So it would have a large RF value. Okay, so now let's talk about solvents. So we said that you're going to have a developing chamber, you're going to put your TLC plate in here, and there's going to be a solvent in here. And then you have to spot your compounds above this, right? So when you put it in, this one has to be above the solvent, so the solvent can just move up and then takes the compound with it. The solvent really matters. Now we're going to learn how to figure out what is the best solvent to use for your TLC. Now, before you can figure out what type of solvent you need to use for your TLC or for any reaction, you need to know about organic solvents. So first, let's learn about organic solvents. What type of solvents will you run into when you work in an organic lab? Alkanes is one type of solvent that is very common in an organic lab. For example, hexanes. You find hexanes in any organic chemistry lab that you walk into. Toluene, also common. Halogenated hydrocarbons. What is that? So those are hydrocarbons that have halogen. An example is DCM. Now, DCM is so common that we just use the acronym all the time. Now, you will know what that means. Dichloromethane. So when someone says DCM, you go, yeah, I know what that is. It's dichloromethane. Chloro, it has two halogen, right? So it's a halogenated hydrocarbon. Now, let's go back to toluene. What's the toluene? It's a benzene ring. Has a metal attached to it, right? Okay. Ether. You know what an ether is, right? Ethyl acetate. What's an ethyl acetate? What type of functional group does it have? Yes, it has an ester, right? So again, I need you to know the structure of all these solvents. Acetone. How about acetone? Acetone is a ketone, right? And I draw the structure because you may have used acetone. You may have used, some people use it all the time. That's nail polish, right? So next time you are using nail polish, I want you to think about it. It's like, oh, this is acetone, which is a ketone. I know what that is. Okay, alcohol. You know what an alcohol is? It has an OH. Acetic acid. You know what acetic acid is? It has a carboxylic acid. Okay. So it's very important for you to know the structure. Let me actually draw the ethyl acetate also. So the ethyl acetate is an ester. Okay. You know what an ether is, you know what an alcohol is. So it really matters to know the structure. Now, I want you to pay attention to this beautiful list that I put down. You probably don't think it's beautiful, but you might in a second. If you look at this list, do you see a pattern? What did I do here? On top is alkanes and hexanes. Bottom, acetic acid. The way I put the list together in the ranking for polarity. See, told is beautiful. Top are the least polar. They have nothing but carbon and hydrogen. Bottom, these are the most polar. So I put them together in the order of polarity because that matters. So you see the solvent, know the structure, know the polarity. Now, I want to give you a side note. So when I took this class a long time ago, this really helped me out. Here's a side note. Hopefully it's going to help you out as well. Remember this. Every time you have nothing but carbon and hydrogen, so you only have carbon and hydrogen, then what you are non-polar. So when you have nothing but carbon and hydrogen, you are non-polar. Now usually when your structure has nitrogen or oxygen, then it becomes polar. So usually when you have oxygen or nitrogen, you become polar. Now, if you have oxygen, you still have a few options. You can be oxygen and you can be an alcohol. You can be an oxygen, you can be in carboxylic acid. You can be an oxygen, you can be ether. You can be an oxygen and you can be a ketone, right? So usually when you have oxygen or nitrogen, you consider polar. Now let's take it one step further. So if you have a carboxylic acid, that is 2 oxygen and alcohol, you are really polar. If you have an alcohol, yeah, you have an OH that has hydrogen bonding. You are also pretty polar. Now when you have a ketone, you don't have the OH anymore, but you have an oxygen. So that's a little bit less polar than alcohol. So by drawing this structure, you can understand the polarity. And I need you to remember this, that carbon and hydrogen, when you have nothing but carbon and hydrogen, you are non-polar. When you have nitrogen and oxygen, usually that makes you to be polar. And then what type of functional group you have with that oxygen will further determine exactly what is your polarity. So far so good? Okay, so these are the common solvent. Know the solvent, know the structure, and you can also look at the polarity based on this. You see OH, oh, that is pretty polar. You see nothing but carbon and hydrogen. Like here, that is pretty non-polar. Okay, so hopefully you got the solvents down. Now, let's go back to what we were trying to figure out. We were trying to figure out what would be a good solvent system for TLC. So what would be considered a good solvent system for TLC? I'm laughing right now because I don't cook, and then one time I wanted to cook, so I called my mom and she said go get a pot, and I asked her what size. She said a good size, and then she asked me to put water in it. I asked her how much water. She said just enough. So I'm gonna be better than my mom in teaching you. Please don't ever tell her that I said that, and teach you what do I mean by a good solvent system for TLC. So to find a good solvent system, first of all, is a trial and error. You just have to try different things until you get a hit and you find one that is good for your system. Now again, so it's a trial and error. Let me write it down. Now, what would be considered a good solvent? A good solvent would give you nice RF. Would give you nice RF values. Now, what do I mean by a nice RF value? A good RF value is usually between 0.25 and 0.35. So you want the RF value to be in the middle. You don't want it to be running off the plate, or you don't want it to not be even moving up at all. So to get the best result, you want a solvent system that is going to give you a nice RF value, and this would be a good range to have a RF value. And also, if you're trying to separate things, you want a solvent system that is going to let you have a nice separation between different compounds. So far, so good? Okay. Now, here's the thing about solvents. If the solvent is too polar, what it's going to do, all the components are going to move really, really fast. So if it's too polar, all compounds are going to move really fast. And we're talking about solvent right now. Now, if the solvent is too non-polar, what that means is all compounds move really, really slow. And we don't want any of these two cases. We don't want it to go fast. We don't want it to go too slow. Because if that's the case, what would happen if those are the case, then you are not going to get a nice separation. We will not get a nice separation. You won't be able to have a good separation between your compounds. So you don't want it to be too polar and you don't want it to be too non-polar. So then how would you do this? It's basically a try and error. You're going to use a solvent. If everything moves up too fast, that means it's too polar. So let's make the solvent more non-polar. If you use a solvent that nothing is really moving, that means it's too non-polar. Let's make it polar. Let's do a practice problem to make sure you're getting the concept down. Let's say I ran 3 TLCs and these are the same compound. Okay, these are all the same compounds. Now one time I ran my TLC using pentane as a solvent. Then I ran again the same exact compound, but I used toluene to run my TLC, and then I used ethyl acetate to run my TLC. After I ran this TLC, then as you can see, when I use ethyl acetate, these went up pretty quickly. And you don't really see much separation between those two compounds. It went up way too high, so they have a high RF value. Now what does this mean? That means this was too polar. So ethyl acetate, too polar, not a good compound. How do I know that? Because the compounds are all moved up too quickly. Now, pentane. Was pentane a good solvent? Not really, right? I mean, even up a little bit, but not really. It didn't go up much. And I don't see a nice separation between these two compounds. You see, you don't really see a nice separation. So this was too non-polar. It was too non-polar because it didn't really get off the plate. It went up, not much, too slow, not much separation. Here, too polar. It went up way too quick and not much separation. How about toluene? Toluene is perfect. Yeah, toluene is perfect. My TLC dots are about 0.25 to 0.35. They're nicely in the middle, and you can see a nice separation between them. So too non-polar of a solvent, too polar of the solvent, but toluene was good. How did I know that? Again, I had to just test it out. That's what we did here is a try and error. You have to try different things to get a nice RF value. And this is a nice RF value. Nice separation between the compounds. They're in the middle of the TLC plate. I consider this A+. Yeah? Okay. Now, sometimes you could also use a mixture of solvents, right? You can mix the solvents together to get the best results that you want. So you can also mix the solvents to get the best result that you want. So hopefully this shows you what I mean by finding the perfect solvent system. It has to be a solvent system that you get a nice RF value and it's a nice separation. If they go up too fast, that means it's too polar. If they don't go up much, that means the solvent was too non-polar and this was a good solvent to use. Nicely in the middle and nice separation. One thing I want you to pay attention to, that when we talk about solvent polarity, that's different than compound polarity. I know your head is probably going, oh. So the solvent polarity is different than the compound polarity. The solvent polarity if the solvent is too polar, it will move everything up too quickly. If the solvent is too non-polar, it doesn't really get the compounds off the base and not much separation. When the solvent is just in the right polarity, you can get a nice in the middle here and nice separation. And again, you have to keep trying different solvent to get one that gives you good result. Now, the compound polarity was different. When you look at these two compounds, I'm going to label them as A and B. Which one of these two compounds are polar and which one is non-polar relative to each other? What do you think? A and B, which one is more polar? A or B? I can't hear you, but answer my question anyway. So A or B, which one is more polar? That's the question. A or B, which one is more polar? The answer is, yeah, A is more polar because we talked about it. When you have a polar compound, it has a smaller RF value than a non-polar compound because the polar compound locks the TLC plate, so it's not going to move up as quick. So in this case, A is going to be more polar than B. I know you're going to get there, and it's a little confusing right now, but just remember for me that the solvent polarity and the compound polarity are two different things. The solvent, you have to find the right solvent polarity that your compounds are going to give you nice RF value in the middle and nice separation. The compound polarity, again, it depends on the more polar the compound is, has a lower RF, and if it's a non-polar compound relative to the other one, it's going to have a larger RF value. Again, when we're talking about this RF value, we're talking about relative to each other, right? So A and B, when we compare these two together, A must be more polar than B. That's why you have a smaller RF value. All right. Really, really nice job. Beautiful.